well, he will say what is the ANDES, Agua Negra Underground Laboratory, experiment site, deep experiment site, by Xavier Bertou from Centro Atómico Bariloche. Thanks.
You hear me correctly? Yeah? Okay, so thanks a lot, Martin, Carla, and all the organizers for the invitation. It's a pleasure to be here and to talk about ANDES. So a project we have to build an underground laboratory not too far from here, just a couple of thousands kilometers. And so I'm going to try to convince you that this is a place where you are going to work in 10 years. For us, when we retire. So this is why I'm especially interested in being here and talking to you. So just to start, a few words about why we go underground. Why do we want these underground laboratories? And this has to do with cosmic rays. I've been working for 20 years in cosmic rays, so I always need to talk about cosmic ray in any presentation. And so cosmic rays, you've probably known a bit about them. So these are basically protons, nuclei from helium to iron mostly, maybe some neutrons, some gammas, which arrive on the top of the atmosphere with high energy. And so they interact in the atmosphere and make a cascade of particles. And in all the zoology of particles which are produced at the level of the ground, most of the things we receive are muons, electrons, positrons, gammas, then some neutrons, a lot of neutrinos, and these kind of things. You may so I'm doing some propaganda. You have already chosen your experiment, so it's not interesting anymore, but anyway. So this is the experiment number 4, where we are doing some cosmic rays upstairs. This is the setup, the final setup that the first 2 groups did not do because we didn't have time, because I talk a lot. You will maybe notice that. And so the next 3 groups will try to reach this state. I'm pretty sure we won't, but anyway. And so cosmic rays are noise. So I've been working 20 years on this fantastic cosmic ray, and now these cosmic rays are the bad guys. They are noise for our detectors. And the reason for that is if you take, well, let's say a big detector, a cubic meter detector here in the university, you will detect every day something like 10 to the 8 muons, 10 to the 8 electromagnetic particles, gammas, electrons, positrons, maybe 10 to the 6 neutrons. And only very few neutrinos, 10 to the minus 3, coming from supernova, even less, maybe 100 of dark matter particle, depends a lot of what kind of particle is dark matter, if it's a particle. And so clearly you have a big signal to noise ratio, very negative for you if you're interested in these guys, in neutrinos and dark matter. And the reason why you detect a lot of these guys and not a lot of these guys is not because there are less of these ones. There are actually much more of these ones than of these ones. But the cross-section, the probability of interacting of the one at the bottom is much lower. So there are weakly interactive particles at best for dark matter. So what happens is that you're dominated by these guys just because they interact much more than these guys. So if you go deep underground, then this problem starts to be an advantage, right? Because these guys will interact in the rock and will not reach your laboratory. While for those guys, there will be no difference. So if you make a big detector underground, you will still have the same number of events from neutrino or dark matter, but you will not have anymore the bad guys, the background, these cosmic rays, right? And so this is what we've been doing for tens of years. So this is one example, Super Kamiokande. It's a 40-meter diameter, 40-meter high cylinder full of water. So this is a small boat. You probably already seen the picture with 2 guys washing the PMTs. Maybe you know the story of the 7,000 PMTs which went pop up in Super Kamiokande. Yes, everybody? No? Well, when they did some routine maintenance of the experiment, legends say it was a postdoc working on one of the PMT. A PMT popped, and it created a wave in the water, and then the second popped, and then the third popped, and 7,000 of them popped out of the 11,000. So I would not have liked to be the guy at that moment. So this happened a year after they got the Nobel Prize, so they could get the money to put them back very easily. That's one of the nice things about having a Nobel Prize. But that's just so to get an idea of the size of this thing, right? And the unusual problems you have sometimes when you're doing experimental physics. things that don't happen in theory. So how deep do you have to go if you want to get rid of this background? So the most penetrating of this cosmic ray is a muon. So usually we are worried about the muon. And so this is a muon flux as a function of the depth in meters of water equivalent. There are a few laboratories on this slide. And so basically at ground level, we have a few hundred per square meter per second of these muons going through Earth. And if you go, for example, at this depth of 5,000 meters equivalent, so that's 1,700 meters of rock, more or less, you get to a rate about 1 per square meter per day. So from 100 per second to 1 per day, now you can work on neutrino or on dark matter with this kind of flux of background. So another way to see it, when we say noise, of course it's noise in the detectors. That's something we all understand. So that's a signal we don't want. When you talk to normal people, you know, there's a guy in the street. Noise is something that you listen to. They have this strange vision of what is noise, and actually you can use that to get an idea of the reduction of the flux of muons. So if you compare what we have here in our experiment, which is about 1 per millisecond per square meter, a little more than that, to what you have in an underground laboratory, for example, Modan at 1,700 meters in France, which is 1 particle per square meter per day. This is exactly the same order of magnitude of reduction of sound of what you have for a rock concert in a big stadium of the best football club in the world, which is River Plate. Compared to Patagonia, where without wind, a place where there is nothing. Actually, Patagonia without wind does not exist, so there is always wind in Patagonia. But if you imagine a place without anything and without wind, then the reduction in the sound is the same thing. So you can say, going underground, we're trying to hear the whispers of the universe. So that's the only poetic part of my talk. Now I will go to something which is a bit less poetic. So that's the list of the talks which were given in one of the underground conference, TAUP, which is a major one, something like 6 years ago. All these talks have something to do with underground laboratories, right? So this is a very active topic, so it was a good idea for you to come to this school. This is something which will give you a likely job in the near future. This is the community is quite mature and a very active community. So what do we do in this underground laboratory? Well, we are doing neutrino physics. You've heard quite a bit about it. I'm not going to talk a lot. So depending on the kind of neutrino you observe, so from nuclear reactors, from particle accelerators, atmospheric, so these are cosmic rays which interact in the atmosphere, right? It's not natural, let's say. Solar neutrinos are produced in the sun, astrophysical, solar is astrophysical, but let's say extrasolar neutrinos, or supernovae, for example, 1989, which was detected, including geoneutrinos. So geoneutrinos are neutrinos which are produced in the Earth. So there is potassium, thorium, uranium, which decays. And the heat which is produced by these decays is supposed to be something like half of the heat produced by the Earth. So it's very important for the geophysicist to understand the thermal balance on the Earth. And so we've been a few years now starting to see these geoneutrinos and put some constraints on geophysics. And so depending on which of these neutrino you observe, you are going to do different physics. So neutrino oscillation, and try to get the masses, nature, Majorana or Dirac, doing astrophysics or doing geophysics. Now a second topic which is done in underground laboratories, on which I'm going to talk a little bit more, because we don't talk a lot about that usually, and it's a bit funny, is multidisciplinary experiments. So it started as a plan B to spend some time out of your usual dark matter or neutrino experiment, but now it's becoming to be a little bit more important, and there are a lot of interesting things going on. So people are doing geoscience. So when you're underground, you don't have high frequency movement from the Earth. So you can do some geoscience that you couldn't do at the surface. You can do some biology, and since you are protected from the cosmic ray radiation, you can measure radioactive components with a very precise measurement that you couldn't do outside. And so this allows you to open some new kind of measurements. I'm going to give some examples of that. For example, heavy metals in plants. So there are some people who think about how can I decontaminate an area by using plants. So there are some plants which, for example, take lead out of the ground. So there could be a way to reduce contamination by planting some specific plant in an area. Now the question is, how do you do that? So how many of them do you plant? How long do you leave them? When do you cut them? When do you replace them? And things like that. And so to do this kind of measurements, you make an experiment, you put some lead, so you have lead-210, which is something very nice for those who want to make lead measurements, which is something very bad when you want to do dark matter measurements, and you use lead as a shield. And so you want to make this measurement, and what people have to do is, so you put lead, you put your plants, you wait 1 day, you cut one plant, you measure the amount of lead in the plant, you wait 2 days, you cut another plant, and you make the measurements, and so on and so forth. If you go underground, you have enough resolution, low enough background, so that you can observe the plant in real time and see how the lead is taken into the plant. So it's a way to understand how these bioremediation processes could be used in real life. Another thing which is related to bio is the impact of cosmic radiation on cells. So we know that when there is too much radiation, it's bad, right? If you fall in a nuclear reactor, you're going to die from radiation before being drawn in this beautiful Cherenkov light, right? But if you go to space also, that's a big problem, radiation. If you go to Mars, you'd better not have a solar explosion while you travel. That's one of the big issues for going to Mars. But what we don't know is what happens if you have less radiation than what we have here, because we always have this radiation. And so people have been doing experiments underground, and actually what they find is that surprisingly, when you're growing cells underground, you reduce the ability of these cells to withstand exposure to DNA damage. So basically what they find is that you need some radiation to train your DNA to repair itself when there is problem. Right? So actually, if you grow cells underground and then expose them to, like we are, where we are, they have more problems than cells which are grown in the outside. So maybe a bit of radiation is good for us. So these are examples of things that are done in underground laboratory. Then there are some even more exotic topics like sardine and anchovy. So people are very interested in this because this is one of the, it's a major economic impact for Peru. And problem is, how do you know the evolution of population of sardine and anchovy over a century? Because you don't have data, you only can ask fishermen, and well, you need to trust a fisherman. Yeah? I used to fish when I was young, and you should never trust a fisherman. So how do you do? Well, people take some sediments into the ocean, and they analyze that, and from that they can know what was the population of sardine and of anchovy at that moment. And what is interesting for them is that they can go up to about 200 years in the past. And with that, they can see how these populations are evolving with the change of the temperature in the ocean. And this is very important given global warming, because this may have a strong impact in the Peruvian economy in the next 10 or 20 years. Right? So this is an example of a very specific measurement which can only be done in an underground laboratory. Then people were looking at the impact of going to leadless gasoline on the contamination in the alpine lakes. And this is also something you can only do in an underground laboratory. And actually they found that when Europe went to get leadless gasoline, the contamination in lead had already been down for 10 years, which is when the US went to leadless gasoline. So probably a good part of the contamination in Europe was coming from the jet stream and from the US. And then just last slides on these funny things you can do underground. So IBM is testing chips to know the real error rate, right? We are making chips always smaller now with this nanometer technology. And so these cosmic rays, when they interact in your chips, they can produce some ionization and make some bit shift. And so you can have some error rates in your chips due to cosmic rays. And so the people who design these new chips to understand what is a real error rate, the zero error rate, not induced by cosmic rays, and then study the one induced by cosmic ray to correct it, do their measurements underground. And then the last thing I'm going to talk about in this multidisciplinary stuff is wine. So wine is very important. I'm Franco-Argentine, so for me wine is extremely important. It's genetic important. Cachaça is important too, but this is acquired experience. Wine is genetic for me. And so there are some people who are selling you wine from the early 20th century. So wine, Bordeaux wine from 1912, which is worth thousands of euros. And so you would like to know if it's really a Bordeaux from the beginning of the 20th century, or if it's a fraud. And if possible, without opening it, because you have to pay before you can open it. So some people thought about measuring these bottles in an underground laboratory and look for cesium. Cesium in the air was only present after the atomic explosions. So before 1945, there is no cesium in air. And after, so this is not cesium, this is strontium, but it's the same, exactly the same curve. You see that it went up very fast, starting from the 1950s, up to a peak in the 60s when the US and the Soviet Union decided to stop making explosion in the air and to do only explosion underground or underwater. And so then it went back down, and now it's going down. And actually, people doing this kind of measure now have also started to see Fukushima. So there is a small spike in the amount of cesium in wine coming from Fukushima. There was an article a few weeks ago about that. So doing this kind of measurement, you can know if a wine was produced before or after 1950s, basically. Okay, now the reason why, well, a lot of us are going underground is to go for the dark side of the universe. Well, you've heard a lot about dark matter, so I'm not going to talk about it. I have a quote from a colleague that he's using a lot from Donald Rumsfeld. It's not, right, you know. There are known knowns, the things we know. There are also known unknowns, right? And the idea is that dark matter is this known unknown, right? So we know there is something, but we don't know what it is, right? There are also unknown unknowns, and as a former mathematician, I have to add that there are also unknown knowns, right? So the things we know, but we don't even realize that we know. Anyway, so for my next talk, I will try to get one from Trump, but it's harder, even harder than Rumsfeld. So there are many evidences for dark matter. The one I like the most is a bullet cluster, so you've seen that. So this is where matter is, this is where, gravity is, this is where gravity is, and this is where normal matter is, so the two galaxies which collide in, and the gas, hot gas producing light. So it really gives you the impression that these galaxies, in addition to this gas, had something which did not interact that much and went along. So this is the current PDG 2018 limit plot. If your favorite experiment is not there, you have to complain to this guy. So my favorite experiment is not there. We have to complain to this guy to add DAMIC, right? It's not there. There is news, so we should have DAMIC on that. And so basically, a lot of experiments are saying there is nothing in the WIMP mass cross-section area above these lines. And there are a few experiments who say, well, I have a candidate, right? So there is CDMS, which has a candidate, but they themselves said later on that, well, it's not a candidate. And there is the famous Dama Libra. So CDMS was a bunch of events that was rejected later on. And Dama Libra is something which has been there for tens of years, and you've already heard about it. So it's a quarter of ton of crystals in Gran Sasso. Used to be the largest underground laboratory in the world, and now it's a Chinese one. And so they observe dark matter not directly, so they cannot separate dark matter from background from the detectors, but they see a modulation. And so basically, so if you have cold dark matter, then the movement of the sun into the galaxy is giving you a wind of WIMPs, and so you're getting a lot of WIMPs in your head as you move with the sun. And so if you move in the same direction of the sun, which is in June, then you are going to get more WIMP wind. And if you're moving in the other direction in December, you are going to get less WIMP. And so this is what they've been observed for tens of years, well, for more than 10 years. This is an old plot, now they have a new one. And of course, well, there are other things which are modulated. For example, muon flux. Muon flux in Gran Sasso, measured by macro, by Boraxino. You see also a very nice annual modulation. And this is basically due to the fact that June is, in the northern hemisphere, summer, middle of summer, and December is the middle of winter. So basically, the atmosphere is different between June and December, right? And cosmic rays are produced in the atmosphere, so what happens at the top of the atmosphere is very important. And this modulates the muon flux, for example. So maybe the muons could explain gamma modulation. Now, if you do the math correctly, you see that the modulation for gamma is offset by 1 month, mostly from the modulation from muons. So there have been a lot of efforts to try to understand gamma, and nobody up to now has managed to convince the community that it's a signal, nor that there is a background which explains it, really. So we are trying hard to do that. And it's so important that it went to the Big Bang Theory, right? So when something goes to the Big Bang Theory, you know, it's important. And this was in the early season of Big Bang Theory. The first one is season 4, chapter 4, when Raj says, I'm telling you, if xenon emits ultraviolet light, then those dark matter experiments must be wrong, right? So the question is not if xenon emits UV light, but the question at that time was, do we understand how much UV light xenon emits when there is an interaction which deposits a small amount of energy? This is a quenching factor. Do we understand properly the quenching factor of xenon at low energy? And so this was rephrased in a way which is easier to understand. And then there is this one which is interesting. Leonard said in season 2 of chapter 15 to his mother, I think you'll find my work pretty interesting. I'm attempting to replicate the dark matter signal found in sodium iodide crystals by the Italians. So that's them. So no reason of research? No. Well, what's the point of me seeing it, right? And so here Leonard was not fast enough. He should have answered. He should have said, but mom, I'm going to do it in the southern hemisphere. And now, if you do it in the southern hemisphere, if it's a genuine dark matter signal, you are going to see the same modulation. Now, if it's an atmospheric effect, you are going to see an opposite modulation. So Leonard was not maybe smart enough, or maybe he knew that there is no observatory, there is no underground laboratory in the southern hemisphere. So this was a situation at the moment of this episode. There are about 12 underground laboratories, and they are all in the northern hemisphere. And this is a situation as of last year, so at TOP from Aldo, where you see still all the laboratories in the northern hemisphere, and the southern hemisphere are just 2 dots in red, which are Future Lab. Sopol in Australia, which is going through a big problem. It should have opened last year, but the mine in which they were supposed to open closed 2 years ago, and so as of today, it's probably not going to open at all. And ANDES, which is what I'm going to talk to you, what I was supposed to talk to you, and what I'm going to talk to you now. So ANDES, what is the idea of ANDES is to take advantage of a tunnel which is going to be built between Argentina and Chile here, so a bit to the north of Santiago, Buenos Aires, and build at the deepest point, which is at 1,750 meters of depth, of rock depth, to build an underground laboratory. So this tunnel is basically for the north of Argentina and the south of Brazil to be connected to Asia, which is a big market. And we want to take this opportunity to have an underground laboratory. So this is a recent history, so a lot of politics in the last 10 years. And basically the important thing is that in 2015, the IDB, the Inter-American Development Bank, accepted to finance the project, which is $1.25 billion. The tunnel, not the lab. And the money is already flowing, even if the lab, the construction has not started, and the international tender is not finished yet. But they already have about a quarter of the money available to start the project. And so it looks like a good opportunity to build in this tunnel an underground laboratory. You can build 2 kinds of laboratories, one in a mine or one in a tunnel. In a mine, you can do it whenever you want, but the access is not very convenient. In a tunnel, it's very nice because you can go with your car, you can go with your truck and your big experiment into the truck. You just have to put it down. But on the other hand, you have to design the lab and to construct it at the same moment as the tunnel is being built. Once the tunnel is open and cars are going through, you cannot build a laboratory inside. So we thought it was a great opportunity to design a big and deep underground laboratory in the southern hemisphere, which would allow us to access with a modulation, to be complementary for supernova neutrino. You want to observe supernova from everywhere on Earth to get some MSW effects, matter effect on neutrino propagation. Geoneutrinos, it's a nice, so this graph, the color is a signal-to-noise ratio for geoneutrinos, and this is a nice red area, while most of the other underground laboratories are places where there are a lot of nuclear power plants. So that's very interesting if you want to see, for example, oscillation from these neutrinos. But if you want to see geoneutrinos, they are a background for your experiment. And it's a geoactive region, which means it's very interesting for the geophysicist. So of course, if you want to make a big dark matter experiment, that is kind of a problem because you have to build it so that it survives an earthquake. So that's something we will have to do. But if you're a geophysicist, it's also interesting to do something else than high energy physics that we are doing. And since the beginning, we wanted it to be an international laboratory, so not only host international experiments, but have the lab itself international, which means that it would be run by Argentina, Chile, which are the two nearby countries, but also by Brazil, Mexico. We are working with Colombia, and also we don't want it to be only Latin America, but we are also in contact with France, Germany, Italy, and the US as of now. So we made some studies, rock studies, to look at the background, the radioactive background, which is okay. Where do we need to put the lab to get the lowest muon flux, depending on how is the mountain? What is neutron activation? Because the lab is at almost 4,000 meters, so it's quite high. And neutron flux can activate your detectors, so they can convert some of the atom of your detector into a radioactive element. So you don't want that to happen. So we made also some studies of that, but it's quite fine. And so this is the muon flux as function of depth. So there are two very deep labs, Snow Lab in Canada and Jinping in China. And then ANDES would be in the second group of lab, like Modan, Baksan, on Dune. So at about 1,700 meters of depth. And then you have another group, which includes Gran Sasso at a lower depth. So it's going to be deeper than Gran Sasso, for example. Scientific program is the one you expect for these underground laboratories, so neutrino physics, dark matter physics, and then this extra multidisciplinary physics. So in neutrino, we would like to host a double beta decay experiment, to have a flagship experiment, which would be a big neutrino detector. Then in dark matter, there is this modulation measurement, then host a fourth generation of experiment, and study new technologies. Geophysics, well, it's a very interesting region. Actually, the way the Chilean plate goes below the Argentine one is special in this area. It's called a flat slab. This is why there are earthquakes on the Argentine side, and not only in Chile as in most of the other part of the border. So the geophysicists are very interested. And then we're thinking about biology, what I told you already, and low radiation measurement. There are also some plans of doing nuclear astrophysics. You can measure with an accelerator underground some fusion processes which happen only, well, interaction, which cross section, which happen only in stars. And so to make these measurements, you need to go underground to get very low background, because you get only one of these interaction after weeks of measurement. So you really need to be underground to kill the background. And this allows you to understand better astrophysics and how the stars, the metallicity of stars, and these kind of things. So I'm not going to enter into details, because it would take too long. And actually, we have a lot of problems at this point, because we don't have the lab already approved. Well, everybody supports it, but the construction has not started. So before construction of the lab starts, it's very difficult to go to an experiment and to tell them, well, would you be interested in going to a lab, which I don't know when it's going to open, but at some point it will open, right? So hopefully next year, construction will start, and we will retake contact with a lot of experiments we've already talked to. So for example, Super Nemo, which is aiming for a double beta decay experiment. We've been talking to people of NEXT last year for their last stage eventually in ANDES. So a large neutrino detector. So should we go for something like a Borexino Camlan scintillator detector in the 3 to 10 kiloton scintillator, or should we go for argon TPC, which looks more promising as a future technology? Then dark matter, so modulation experiment, also fourth generation, and go for new technology. So this is a DAMIC. You have a CCDX lab at the school, so I guess half of you are going to play with these fantastic detectors. Last year we also discussed with the people of Dark Side for their last step, which I would expect to go to Gran Sasso, but who knows? So these are all the things we will have to discuss in the next 10 years, and for which I expect you, as postdocs in these experiments, to convince the spokesperson of the experiment that ANDES would be a fantastic place to install their experiment. So this is what I told you about nuclear astrophysics, so how you measure cross sections in the gamma of peak area, which is what is relevant for in astrophysics. So this was the plan we had in 2011 when we started for ANDES, so 2 tunnels, and you would go into the lab with a very big hole, an intermediate hole, and a big pit, and a few small caves. And this is a design that we have right now, which is not very different. So this is a big hole, this is intermediate hole, this is a big pit, and there are still a few small rooms all over the place. So we plan for a main hall of 20 meters by 23 by 50 meters, so that's quite big, right? 20 meters is maybe 5 floors building, right? So it's a significant size. It's about half a Grand Sasso hall in size. Then secondary halls and a lot of small halls, and a big pit for a big experiment, probably a neutrino experiment, 30 meters of diameter and 30 meters of depth. And the cost estimated by the firm who did all the work for the tunnel is about $38 million. So that's less than 2.5% of the tunnel cost. And our plan is to have this included into the building of the tunnel, so that all the civil work would not have to be paid by science money, but just by every Argentine and Chilean money to the IDB. To get an idea of the size of ANDES, so this is the Japanese lab, so this will be Dune in some way, so this is Gran Sasso, and this would be ANDES. So it will already be a significant lab. It will be about twice larger than Snow Lab, so it's a significant amount of space that would be available for in the Southern Hemisphere. So we are actually working as we speak, as I speak. You don't speak, right? You're listening, that's nice, thank you. So as I speak, we are working on the design. So this is a conceptual design. We are working on a technical design for this to be included in the civil work. And so we've already added this big part, which is a geophysics part. And we are moving some of the caves, and we are removing some of the tunnels to keep the cost as close as possible to the $40 million. While adding this possibility to do multidisciplinary physics, since we started with thinking mostly of what we want to do and not what the other guys want to do. And since it's in the mountain and basically in the middle of nowhere, you don't want to spend your whole life there, especially without windows. So usually you go to work maybe a few hours or a few days, but then you go back to a normal laboratory in a normal town, or at least as normal as possible. And so we plan to have one support laboratories in all the underground laboratories, one in Chile, in La Serena, which is a bit far from the lab, but which is a big city where there is the European Southern Observatory base, so there is a lot of scientific activities, and then have maybe a smaller but closer laboratory for the operation, day-to-day operation, and this will be, of course, linked to the local university, visitor centers, and these kind of things. So we got a lot of support from a lot of people. So here we have two Nobel Prize, Kashita and MacDonald. We got the support of the binational entity, which is in charge of the tunnel, both politically and technically, so this was extremely important to allow us to go on. And then of basically any scientifically related agency in Argentina and Chile to push for the tunnel, plus some contacts in Latin America. So there was Ron when he was, he was vice director of the SBF, which is not longer, but still director of the CBPF. And in addition to the guy who said it would be great to have ANDES, this is a list of the guy who said that they would be happy to work in ANDES. So in 10 years when we open ANDES, I will go back to their office and say, come and do what you said you would do. And so you see the 4 countries we've been working mostly up to now are Argentina, Brazil, Chile, and Mexico. So Brazil is a big part of the project that we've advanced up to now. So our timeline up to now. So we started in July 2010 in my office. At that time, we didn't know exactly what we were going to do. But we got very positive feedback from a lot of people. First our colleagues and the community in Argentina, in Chile, in Brazil, in Mexico, which are the communities we had contact with. And then with the international community. And so after that, we had a few workshops, one in Argentina, then in Brazil, then in Chile. We got approved by the Ministry for Science in Argentina and by this binational entity in March 2012. So this was really a big step. Then we had a workshop in Mexico where we created a unit into the Latin American Center for Physics, which allows us to pay for the things we need to pay for ANDES. We had this conceptual design. You've seen the drawing 2 years ago done by the company who's designing the tunnel. So this allows the thing to be integrated. And after our last workshop in Buenos Aires, the EBITAN approved including ANDES into the Agua Negra tunnel, but we need the detailed engineering study to be done. And so we started it a month ago. It's about $500,000. We got the money from San Juan, and so we should finish that within 2 months. And after these 2 months, the design will go into the civil work of the tunnel. And in 2019, if everything goes well, the company to build the tunnel and the lab will be chosen, and then we will just have to wait for 2027 for the lab to open. So 2027 is in 10 years. Yeah, probably won't be 2027, probably 28, 29 maybe. So what do we do meanwhile? So of course we have to plan what is going to go into ANDES. And so we are working on damming in Snow Lab, and we're working in Coney and other experiments in other underground laboratories. But it would be nice to have an underground laboratory in the region, right? So that we could test our capability of building these kind of things locally. And so this is what we've just starting to do recently, which is to think about Sierra Grande. So Sierra Grande is a mine in Argentina, here. So we are here. This is São Paulo, right? Buenos Aires, Santiago. This is Bariloche. This is where I work. That's why this small spot. And so Sierra Grande was an underground laboratory which was operating in the 1990s in Argentina for a few years in a mine, but then the mine closed, and so they had to close the lab. And it was basically the idea was from Frank Avignone to make an experiment with Juan Collar, who's now a colleague in some of our experiments, to measure a daily dark matter modulation. So it's kind of different from the one from DAMA, which is yearly. Now the idea is a daily one. The reason for that is so the WIMP wind is coming from Cygnus. Cygnus is something like 40 degrees of latitude north. So if the WIMPs are interacting with the Earth, for example, they are losing energy when they cross the Earth, or if there is some dark matter inside the Earth and the dark matter is self-interacting, then you would expect to get a different wind WIMP if you observe directly Cygnus or if you observe Cygnus through the Earth. And so this effect is maximum if you go on the opposite side of Cygnus on the Earth, which is 40 degrees of latitude south, which is exactly where Sierra Grande is. And actually, that's also one of the reasons for SUPPLE in Australia to be built there. So in the 1960s, they made an experiment. In the 1990s, they made an experiment. They had some wrong calculations. So this was 2 orders of magnitude wrong, and so that's 4 orders of magnitude in size of the experiment wrong. So they didn't measure anything. But it was for a few years they had access to this place. They installed a lab which they had to dismantle, and it's 400 meters deep. It's not very deep, but it's still 1,000 meters of water equivalent. So it's better than nothing. And here you have a few papers. So this one, and here I put the archive, which are easier to access than the other one, but some of them are PRL, and so they are real paper, real physics paper. And so when you get to the place, so this is a mine. So this is the shaft of the mine. So this is where what you normally use to get into the mine. But since the mine is not operating anymore, they are just in maintenance. It is not used, but you can access to the mine by this tunnel. And so you go with your truck, and you arrive there, which is where the experiment was 20 years ago. And this is a car, right? So that's very convenient, because if you have your experiment, you can put it on a trailer, and you drive 10 minutes, and you arrive there, you put your experiment. You don't see it, but over there, you have power and communication. So 60 meters from the site, you can plug your experiment, you can plug your Ethernet cable, and have your experiment up and running. And so just to show you that we already were there. So this is Horacio, who's doing the Silicon PM lab. You can, sorry, and I'm also on the pictures. This is me. So this shadow is me. The master puppet always stays in the shadow. So. So this is Sierra Grande. It's not as deep as any of the typical underground laboratory, but it's there, right? It's close from any one of us in Latin America. It's especially close from Bariloche. It's only 700 kilometers of drive when the road is not cut because of snow. So it's almost close for us. And so the flux, the muon flux should be, we'll have to measure that, but should be around 2 per square meter per minute. Compared to 100 per second, it's already a reasonable decrease in the muon flux. So there are some kind of experiments you could do there, especially if you want to see this daily modulation, and especially if you don't have a detector which is too big, right? When you have a small detector, then you're not, the background is usually not a problem, because it's unlikely for something to hit your detector. Right? When you get a bigger detector, then you get more background. So the schedule we have for Sierra Grande, so we had our first trip and contact 2 weeks ago, so it's really, right, just happening just now. So the president from the mining company, which is Chinese, very funny guy, was extremely happy with what we were proposing. So he's writing a letter of interest that we are circulating right now among us to sign, to tell us that he would like us to go and work there. And then we will sign an official agreement between the Atomic Energy Commission in Argentina, which is where I work, and the Chinese company in the next 2 months. And we hope to go back to the place in September to make a muon flux and radon measurement. And then we have a very aggressive schedule in December to install a first experiment there. We already have part of the experiment running in Bariloche for test and calibration. So it should be feasible to go there, I guess. The politics will delay it a bit. But anyway. The site will likely be available for 5 years. If everything goes well for the company, in 2 years they will start operation of the mine again, and it will take 3 years before they reach where we are, and at that time we will have to move. And at that time probably we will have to move 100 meters up, and then we could stay there for forever. If the iron price, because it's an iron mine, does not go up, then we may have more than 5 years in the place. And this is probably something we will want to use also to develop new skills underground, like copper electroforming or start multidisciplinary science. But that's something we still have to discuss with the mine, as we just discussed the basic experiment, which is this experiment to start at the end of the year and to have it running in the site for 6 months. And this is what they agreed on. So to conclude, if you're interested in ANDES, so of course you can come and talk to me, but you can also stay for just a few more days after the school, since on the lovely Saturday and Sunday and Monday we are going to have this workshop. I did not choose a date. So here at the ICTP site. So we will have 3 days to discuss about the lab, about some politics of the lab, so that's maybe not the most interesting part for you, and also about the role of Brazil in the collaboration, so that might be interesting for at least half of you. And well, that's it. I hope I've convinced you that we are faced with a great opportunity to build a world-class deep underground laboratory, one of its kind, or maybe the only one in the Southern Hemisphere, operated by international consortium, a place for you to work in 10 years. And I'll finish with these paintings from an artist who's doing painting related to science. So this is Neutrino Search, which I've discussed with her. She's quite interesting artist. Thank you very much.
So we have time for questions.
Yeah, the whole lab is located in a region with a lot of seismic activity. So how this is going to affect any precision measurement?
So it's when you design your experiment, you have to take that into account. Yeah. So if you're underground, then you're not as sensitive as if you're outside. If you're outside, you have this very high frequency wave, S and P waves, which are the ones which are destroying the buildings. And so this is where you don't want to be. Now when you're underground, these waves are damped into the rock. And so basically what happens when you're underground is that the whole lab is moving on one side and then moving on the other side, right? So nothing breaks. Now the problem is when you design your detector and you have a big water volume with a big xenon or whatever inside, then it moves on one side, and then you have to make sure that it moves on the other side and that it doesn't go in the same direction with its impulse, right? So you design that on a structure which allows you for this kind of movement. This is something which is well known, and actually for example, in Snow Lab, you have to do the same thing, because in Snow Lab, it's mining which is in operation. And so sometimes they have a small earthquake of 4 magnitude, but which is close by. So this is something, it is a pain, but it is something which is known, and you know how to deal with it.
Okay.
Hello. What about the funding? You said what about the funding?
Good question. So at the end of the talk, I will come with for donations. You're all welcome. Every real counts. So what we have right now is an agreement from all the members of the EBITAN. So it's a political entity. So it has been approved by the Congress of both countries. So it's the highest level of entity you can have internationally in the 2 countries. To have the civil cost included into the IDB land for the tunnel. So the $29 million of the civil work and the $10 million of the electromechanical, so ventilation and things like that, should be paid by the IDB. So we only have to pay for the scientific part. So the scientific equipment of the lab itself and construction of the support lab is something we will have to pay from science money. So for that, for the laboratories, this is something we want to do locally. So this will be Chile for La Serena, and this will be Argentina for San Juan. And this will probably come mainly from the province, which have a huge interest of having these things in their region. And then for the lab itself, for the scientific equipment of the lab, this is where we want to build an international consortium. Since we have 10 years to build that, in fact, if you divide the $10–15 million for the basic equipment among 10 years and among 6–7 countries, this is really peanuts, right? So we have to make these international structures. That's what we are going to discuss in 3 days, well, on Sunday, based on some CERN-like structure, which is called Sesame in Jordania, which has exactly the structure we need. And once we have this structure, then have commitment from the various countries to put something like $300,000 per year during the 10 years of the construction of the lab. And this would allow us to have the lab equipped without any experiments, right? So this is just a lab. Then, of course, you have to make the experiments. That's your problem. My problem also.
So are there any interesting neutrino oscillation experiments you can do with the baseline from ANDES to Fermilab or CERN or somewhere else?
There was. It was a magic distance when you wanted to measure theta 1,3. And so when theta 1,3 was small and small and small, and nobody knew if you could measure it, then there was this 7,500 kilometers from Fermilab to ANDES, which was a magic baseline. Well, it's not easy to have a beam for this distance, but there was this. And then Dajabet told us that it wasn't that small, so this disappeared. I didn't check if it's a relevant distance for delta CP or this kind of measurement. But I mean, given what Dajabet has seen and what Juno is and Dune, I don't think there is anything I can think of as of today to exploit this baseline. Then from Kamiokande, from Keck, you will go through the center of the Earth.
That sounds exciting.
But you have to build a 100-meter pipe up and then go 100-meter pipe down and point your neutrino beam at I don't know which fraction of a degree to get ANDES. It would be challenging.
Hi, I believe in 10 years from now, the mixing angles will be measured with quite good precise. The hierarchy problem of the neutrinos, I think, will be determined, and the double beta decay experiment will determine the Majorana or Dirac particles. So, in 10 years from now, which open question from neutrino science will be possible to answer with ANDES? Yeah, so hopefully these three questions will be answered in 10 years. So as I put in my slides, what we aim to in ANDES would be low energy neutrino interaction, and so one of the things we could do is supernova neutrinos. So when you have supernova neutrinos, you need a network of detectors on 100% of the time, because you never know when it's going to happen. And then if you want to study the interaction of the propagation of neutrino in matter, then you want to have a few detectors who can observe the supernova directly, and then a few detectors who observe it through the Earth, so that you can study these effects. And then there is the geoneutrino, which for most of the current experiments have a big background from nuclear plants, and which have no background in ANDES. But these are not top project. I mean, I fully agree with you that within 10 years, neutrino physics will be interesting to do, but will not be a Nobel Prize as we are right now waiting for double beta decay or the mass hierarchy and mass values.
The history of physics usually tells us that when we think that everything will be done, things get more and more complicated, but let's see, right?
Yeah, whenever you have an answer to a question, you are disappointed, right? As a physicist, you're not looking for answers, you're looking for questions. So hopefully with all these answers will come new questions, right?
More questions? So just a comment about funding, because if we were having this discussion like 5 years ago in Brazil, people would say, yeah, let's put a lot of money there. We were discussing ESO, CERN, Sirius, and many other things, and now we have so many cut fundings that we think, wow, we are Brazil, Argentina, perhaps Mexico. We don't have money, but this is a time scale where I'm not economist, but this is a time scale that history tells us that we can have money, so we have to plan now. And São Paulo, especially where we are, it's putting $40 million just to pay cash for a big telescope, with not, big science in return, which is nice. But a lab like this develops, having a lot of people involved, developing instrumentation, so on. So the return is way bigger. So we have to think big. We don't have to be shy because we are in a bad moment. And vote well because, you decide the history of this country. So, also a comment about the dates. Yeah, it's a weekend. That's not bad, but that's our to blame on us. So we wanted people on this school to be able to participate in the workshop. So that was the whole idea of setting the dates right after. So many of you are already registered in the workshop, and okay. But if any of you want to participate, just contact us. If you are from São Paulo, that's very easy. If you are not, and maybe you need a little bit of funding, maybe we can work this out. So if you are interested in participating in the workshop and you did not register, look after him or me or Carla or anyone from the, the organization of these two events that we will try to make this happen, right? Any other question? Okay, okay. As I have the microphone, a second question, a second comment. In Chile, there are more than half of the biggest telescopes in the world, and now astronomy is booming in Chile. You may correct me if I'm wrong. Namibia has a great gamma ray observatory. As far as I know, nothing is happening there. So it's up to us to take this great opportunity. I think this lab will be, a fantastic lab, and of course Xavier has shown us why. Perhaps, this will be used by just, northern people again, which is fine, but will not be very involved. Or we can take a more active role, and maybe like in Chile, they were very smart on how they made the agreements. So we have to try to be smart in a way that we can take profit from having this lab nearby to develop science, So that's the reason of the workshop too. So we'll be discussing this during these days. But I mean, it's good to have this in mind. Like, time scales may sound, a bit large. As a student, I can guarantee you that this was very fast. When I was a student, I was attending a CMB course about the Planck and WMAP, and those things seemed so far in the past. I personally was not very interested. I said, wow, WMAP, Planck, and now we have a lot of fantastic data from these experiments. So we really have to think ahead and prepare. So you guys, the young faces I see, are like the ideal people to be prepared to do science in this lab. So I hope you do participate, or if you cannot participate in the workshop, be aware of this. I think that we can take this opportunity to be a big thing for Latin America, okay? All right, more questions? Okay, so let's thank the speaker again.